This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on tangents to polar graphs. Let's re-examine the parametric equations. From Leibniz notation, we know slope is dy dx. With parametrics, we're given y as a function of t, we're given x as a function of t. So dy dx is simply dy dt divided by dx dt. Looking at an example, if we have x of t is t squared plus 4t plus 5, and y of t is 2t cubed plus 3t, the numerator is dy dt, which would be 6t squared plus 3. The denominator is dx dt, which is 2t plus 4. We want to find the slope of the tangent at t equals 1 in our example, so we would plug 1 into those values. So our dy dx at t equals 1 is dy dt divided by dx dt at t equals 1. 6t squared plus 3 over 2t plus 4 at t equals 1. Plugging 1 in for t, you can see we have 6 times 1 squared plus 3 over 2 times 1 plus 4, 9/6, which of course reduces to 3/2. So that's our approach to find the slope of the tangent for a parametric equation. What we're going to be given here is a polar equation, and one of our goals is going to be to convert that polar equation to a parametric form. So here's what we'll start with. We want to find the slope of the tangent to r equals 3 sine 2 theta at t equals pi over 3. So I've graphed that polar curve, that rose. The point of interest is pi over 3, so 60 degrees up from the x-axis. So there's the point on the curve. We want to find the slope of the tangent at that point. Just sort of drawing it in by hand here, you can see that the slope of the tangent is a positive number. Looks like it's maybe smaller than 1, just to kind of eyeball it, but it's some sort of a positive number. We want to find that slope of the tangent. We're going to use parametric representation to get there. So again, here's our question. And how do we convert a polar equation into a parametric one? What's our strategy? What are the techniques that we need to do that? Well, we remember from our triangle that x is r cos theta and y is r sine theta. So you can see we know what r is. R is 3 sine 2 theta. Replacing this r with 3 sine 2 theta, replacing that r with 3 sine 2 theta, will be a way for us to express x and y in parametric form using theta as the variable. But we want to use t. So let's go through the process of using t to express this in parametric form. So here's our theta form. X of theta is r of theta cos theta. Y of theta is r of theta sine theta. So just replacing theta with t, we've now rewritten this as a parametric representation with the variable of t. So that x of t becomes r of t cos t, y of t becomes r of t sine t. Just to be consistent with our notation working in the parametric world. Now, in parametrics, dy dx is dy dt over dx dt. So I'm going to need to figure out what is dy dt and what is dx dt. So think about the sort of approach we're going to use to get there. Again, here's our problem. Here's our x of t and our y of t. And we have to find dx dt. And the strategy we'll use is the product rule. Derivative of the first, r prime of t times the second times cos t, plus r of t times the derivative of cos, which is minus sine t. And we have our representation for dx dt. Similarly, for dy dt, the derivative of the first, r prime of t times sine t, plus r of t times the derivative of the second is cos t. So we now have representations for dx dt and for dy dt. The slope, of course, dy dx is dy dt divided by dx dt. dy dt, this thing, r prime of t sine t plus r of t cos t, that's our numerator. Dx dt, here, r prime of t cos t minus r of t sine t is our denominator. And this is a formula that we can use to determine the slope of the tangent line for a polar graph. But as you can see, it's fairly easy to derive. Again, this is our question. Slope of the tangent to r equals 3 sine 2 theta at t equals pi over 3. Now, we're going to need to have the derivative of r. So r as a function of theta is 3 sine 2 theta. The derivative of sine 2 theta is cos 2 theta times 2, so that the derivative of r with respect to theta is 6 cos 2 theta. But on the previous page, I was using t. So instead of r prime of theta, let's think of it as r prime of t. So r prime of t is just 6 cos of 2t. All we're doing is replacing the theta with the t. Now, there's the formula I had on the previous page. So r prime of t now is 6 cos t times that sine t plus, now what is r of t? Well, if r of theta is 3 sine 2 theta, r of t is just 3 sine 2t times cos t. In the denominator again, r prime of t, 6 cos 2t times cos t minus r of t, again, r of theta, 3 sine 2 theta, r of t, 3 sine 2t times sine t. So this is what we need for our example to find the slope of the tangent line at t equals pi over 3. So now we have to just compute, replacing t with pi over 3 in 8 different places. 2 times pi over 3, of course, is 2 pi over 3. So 4 of them will be 2 pi over 3, and 4 of them will be pi over 3. And then we need to evaluate the trigonometry. So doing that substitution, the slope at t equals pi over 3, 6 cos 2 pi over 3, sine pi over 3, plus 3 sine 2 pi over 3, cos pi over 3, divided by 6 cos 2 pi over 3, cos pi over 3, minus 3 sine 2 pi over 3, sine pi over 3. Remember, of course, 2 pi over 3 is in the second quadrant. In the second quadrant, cosine is negative. So this number will be negative, this will be negative. 2 pi over 3 is in the second quadrant, but sine is positive. So this number will be positive, and this number will be positive. Reference angles for all of these are the same. Always pi over 3. Sine of pi over 3, root 3 over 2. Cos of pi over 3 is a half. So keeping that in mind, and keeping in mind the quadrants, we should be able to do the computation here. So again, this is what we're starting with. Plugging in those values, what do we get? Cos of 2 pi over 3, negative 1/2, quadrant 2. Sine of pi over 3, root 3 over 2. Sine of 2 pi over 3, also root 3 over 2 in quadrant 2. Cos of pi over 3 in quadrant 1 is a half. Cos of 2 pi over 3, quadrant 2, negative a half. Cos of pi over 3 is a half. Sine of 2 pi over 3, root 3 over 2. Sine of pi over 3, root 3 over 2. So to simplify this in arithmetic, numerator for this first piece, negative 6 root 3 over 4. Numerator for this piece, 3 root 3 over 4. Numerator for this piece, negative 6, denominator is 4. This piece, root 3 times root 3 is 3, times 3 is 9 over 4, or minus 9/4. So looking at the computation then, we get negative 6 root 3 over 4 plus 3 root 3 over 4, and the bottom, negative 6/4 minus 9/4. Lots of common denominators, so the computation's not so bad. What do we get? Negative 6 root 3 over 4 plus 3 root 3 over 4 is negative 3 root 3 over 4. Negative 6 over 4 minus 9 over 4, negative 15 over 4. Multiply numerator and denominator by 4. That clears the fractions, or invert and multiply. So take that numerator fraction, multiply that by 4 over negative 15, and you will get negative 3 root 3 over negative 15. and then reducing that fraction, dividing top and bottom by -3, and we get √3/5, which is a positive number. Recall when we looked at the first picture, it appeared as if the slope of the tangent line was a positive number. The tangent line was increasing from left to right. So that at least gives us some verification that we're at least on the right path. And as we look at that, you can see there's the slope of our tangent line. There's our tangent line with a positive slope. Well, as long as we have the slope, let's find the equation of the tangent line. But to find the equation, you need to have the point x and y together with the slope. We have the slope. Now, this point that I have here is in polar coordinates. That's at t equals pi/3. 2 times pi/3 is 2 pi/3. The sine of that is √3/2 times 3. I have r is 3√3/2 when we are at pi/3. Now you'll notice I'm using t here rather than theta because I'm considering this from the perspective of the parametric representation. So recall that x is r cos theta and y is r sine theta. So r 3 sine 2 theta times cos theta, y 3 sine 2 theta times sine theta. Just replacing that r function in for r here. Now our t, or actually our theta, would have been a better representation here, so I guess maybe I'll change it now. So what do we have here? X is 3 sine 2 theta cos theta, and y is 3 sine 2 theta sine theta. Replacing theta is pi/3, we get that. Of course, the sine of 2 pi/3 is √3/2, and the cos of pi/3 is 1/2. Sine of pi/3 also √3/2. So making those substitutions, our x value is 3√3/4, and our y value, √3 times √3 is 3, times 3 is 9, 9/4. So we have the point xy, and we have the slope m. That's enough for us to find the equation of the tangent line, which is what we're looking for. So we have those three values. If I have the x and y value together with m, how do I go ahead and find the equation of the tangent line? Well, we like to use this formula, the point-slope form, namely y minus y naught equals m times x minus x naught. And for clarification, notice the x that I had given you, I'm now calling x naught. That is our given x value, not our changing x value. This is perceived as a changing x value. That's a changing y value. Again, our original y is now y naught is 9/4. So using point-slope form, we get y minus y naught is m times x minus x naught. Substituting y minus y naught, y minus 9/4 equals m √3/5 times x minus x naught, x minus 3√3/4. And that gives us our final equation. And then to finish this, I graphed the original rose petal function, polar function, together with the point and the tangent line with this tangent line. And what does that look like? There we go. There's our rose. There's pi/3, 60 degrees from the x-axis. There is our tangent line with the slope of √3/5 through that point. And again, indeed, notice that that tangent line has a positive slope. And that will conclude this lesson.